So now we will go to an important topic called as the processor design. We have understood that how a machine language instructions are very important to implement any task on the given processor. Now, given any machine language instructions, we should be able to understand that how that machine language instructions are executed inside the processor, given the processor hardware details. How the processor companies will design inside the processor so that they can able to execute the different instructions supported by the given processor. When I say processor design, we require the principles of synchronous sequential circuit like a flip-flop, registers, counters is required. We require the knowledge of combinational circuits like adder, subtractor, comparators, all this is required. The complete knowledge of sequential, both synchronous and asynchronous and hardware combination circuit are required to design the CPU. So let's start understanding how the CPUs can be designed and how instructions are executed inside that one. So now what is our purpose? So we should be able to learn how completely processor is being, what is present inside the processor, that is different blocks, how they are connected. If I give one instruction, any one of the instruction in the machine level language, how these instructions will be executed, execution done here. So I should be able to support. So here I should know two things. One is I should know the complete hardware of this processor. So sometimes we call it a firmware, because why? Sometimes micro instructions are being put inside the processor. So in such cases, its hardware comes software. And also I should be able to know all the instructions, the meaning of the instructions, the operands, addressing modes. So the flags, all these concepts are also required to design the processor. So that's why the processor designer should have the knowledge of assembly level language, instructions, how to write a program, and also they should have the knowledge about digital electronics, that is combinational and sequential circuits. Only when both are available, we can able to design our own processor. So when I say design a processor, thousands of engineers will be there in Intel teams to design a processor. So as an individual, within a short time, you cannot design such a complicated processor, but we can design a simple processor which contains all important components required for a processor. So the basic concepts of processor design we will be able to understand. So that is the principle of this lecture. So now let's understand what is there in a processor. First of all, any processor you take it, basically processor comprised of these particular blocks will be there inside a processor. So I'm just taken a processor. So a processor will not exist. That means there is no meaning for the processor unless the memory is available. So I'm just putting a memory along with the processor. Now I'm just showing what are the connections will exist from memory to the processor and what are the important blocks present inside the processor before we go to the little more details about the processor. So as we understood that the memory supports three types of memory and the processor supports three types of buses. One is called as an address bus, so which is connected inside the processor by a register called MEAR, memory address register. Memory also supports, there's another bus called as data bus, which interfaces between the memory and the processor. So any data transfer between the processor and the memory should happen through this bus. There is a separate register is provided inside the processor to support this communication memory data register. So memory address register and memory data register, the two registers which differentiates between the two buses, because this bus what is available is present, we call it an external bus, a bus or a set of lines which is present outside the chip. Inside the chip there is a bus is there which communicates between the different blocks what is present inside, that is we call as an internal bus. So always when you do a processor design, we should always understand that there are two buses are there. One is the bus which facilitates communication between the processor and to the memory and to the input devices. A bus which is present inside the processor which establishes a communication between the different blocks what is present inside the processor. So after the memory address register always is the one which is responsible to generate or put an address on the address bus. So you can generate an address from a register called as a program counter. A program counter, we know that it's the one which generates an address where from which fetch the instruction to be executed. Or we can also, if you want to read a data from a memory, the registers also can be used to put the address into this memory address register, because we know that register holds both the data and a pointer also. So the contents of the MER can come from a PC or from a registers. Let's say R02 or N-1, some N registers are available. And apart from that, the processor also will have a special register called instruction register. As soon as you bring the data from a memory, so any data which comes into the processor should come first into the MDR register, memory data register. From there, I can bring the data to the instruction register if it is an instruction. If it is not an instruction, I am bringing from memory is a data, then I can put the data into any one of this register. So instruction register holds the instruction once you get into the processor, which gives all the signals to the control and decoding circuits. So which is the one which gives all the information to the control decoding blocks, which generates lot of signals inside and outside also. So we have also a bus called as control bus, which contains a read, write, memory function complete, all those signals which are generated by the control decoding circuit. Control decoding circuit also generate number of signals inside to coordinate the work. And apart from this, there is a block called as ALU, which is nothing but a pure combination circuit which contains adder, subtract, and everything, which is capable of performing all arithmetic and logical operations. So these are the blocks which are generally present inside the processor. Now we will go into the details now again. Little more details we'll go that now. Now, so I'm going to, am I audible? Am I audible? Am I audible?
Yes, sir.
Yeah. So now we will go to the little more details about the processor. So now I given a just overview about how the processor and the memory interface is there. Now, since we are designing the processor now, I am going to write now the different blocks of the processor and their interconnections. So I have chosen a basic organization. That basic organization of a processor we call as a single bus organization. Single bus organization, when I say, that means that there is a one internal bus is available, which establishes connection between all the blocks available here. Now we will design the processor using a single bus organization now. So since now I'm expanding what is present inside the processor, I'm writing all the blocks and the interconnections now. So this is an internal bus. The size of the internal bus is always the size of the word length. If the processor is 32-bit, the size of the internal bus is also 32-bit. Now, the first block, what is present inside the processor is the program counter. So program counter direction is bidirectional. That means that when you execute instruction called branch greater than 0, the program counter can be written also. So otherwise, program counter contents will be always brought out through a MER register for generating the address where I have to fetch an instruction. Now, there are two registers we have studied which are important to establish an interface to the memory. One is called memory address register, that is called as a MDR register, memory data register. MER register has got one input and one output. So that means that you can write into the memory address register either from the program counter or from other registers. You can write, and the contents of that we can output it to the bus, the memory bus, external bus. We can able to do it. So it's one input, one output. Whereas MDR has got two inputs and two outputs. So what are the two inputs? That means that you can write into the MDR register from outside, from memory to MDR register. Also, when I am writing the data from the processor to the memory, also you can write to the MDR. Either you can write from the processor to the memory, one method of input is possible. When you read from memory, reading from memory to the processor, there's another direction possible. That is why we say two inputs are there. Similarly, two outputs. You can send the data from processor to the memory, or you can able to do the other direction also. So MDR supports two inputs and two outputs. Two inputs are what? One is a processor, other is a memory. Two outputs again what? One is a processor, other is a memory. Both direction is possible. Now, apart from this, we have what is called as ALU is available. ALU is available. Now, this ALU, any ALU you take, basically it comprises of two basic operands will be there. A operand and the B operand will be available, and it provides the result. Now, so since there is only one bus is available, we should understand that only two blocks, two entities inside the CPU can only communicate. We will just finish other entities and then come back to the ALU. Now, Apart from the ALU, you have a set of registers are available inside the processor. These registers are the size is equivalent to 32 bits. The word length is 32 bit. Now, all the registers, I'll name them as R02 or N-1, where N is a number of registers. Now, all these set of registers will be called by a popular name called registered file. So registered file is a collection of all the registers present inside the processor. It is nothing but a RAM memory. It's nothing but a cache memory. But only thing is they have a unique naming is there. When I say memory, we talk about address. When I talk about register, there is a unique name for every register, R0, R1 like that. You don't require to specify like a address. We just say R0, but encoding happens in the form of address inside. Now, so these register file then contains the registers which are called as general purpose registers. So general purpose register means these registers are available to the programmer either to keep the data or to keep the pointer, to keep the temporary storage is left to the programmer to declare the variables, allocate them to the variables. So the way the programmer thinks, he can use all these registers. Now, so the processor also provides one register. We have discussed that it's called instruction register, which holds the instruction as soon as you bring instruction into the processor. So it is an input. So the moment you get an instruction into the processor, we bring that instruction and place it in the instruction register. What is the job of instruction register? Instruction register, with the help of decoder and control logic, should identify what is the meaning of the instruction. So that is why instruction register output is always connected to the decoder. Instruction decoder, that is decoder means it identifies the meaning what is present inside the instruction, because instruction is basically in binary format, ones and zeros. So these ones and zeros decode some information. If there are 3 bits are there, 2 to the power of 3, 8 meanings it can able to encode. That means the decoder is the one which looks at bits and decode what is the information which is encoded in these bits. Instruction decoder and control logic is being present, which is always the is connected to the instruction register. These instruction register will generate lot of control signals. Some of these control signals will goes to the memory, that is externally memory and IO devices, input output devices, and other control signals are connected to the different blocks what is present inside the processor. Instruction register sometimes also being connected to the bus. You may ask a question, why instruction register has to connect to the bus? Whenever we execute a branch instruction like that, I told in the last session, we are encoding the displacement is also part of the instruction. In such cases, instruction register will extract that X value, which is a part of the instruction, and puts into the program counter, add to the program counter. Now, in case of a relative addressing, it's basically contents of program counter plus X to be added. In such cases, I require the contents of instruction decoder should extract that information and add to the PC. So that's why we'll write this direction also, we'll able to write it. Now all the registers which are present here are bidirectional in the sense I can write into the register, I can read from a register also. Now we'll come back to the ALU logic now. ALU requires 2 operands at a time to perform the addition and give the answer back into the processor. But this bus, what the bus we have now, this bus is only one, in the sense only one at a time, one communication at a time can happen. That means that I can use this bus to either transfer the data from register to program counter, or I can use this bus to put some data from MDR into the register. Any one communication can happen because the only one bus is available now. But ALU requires 2 operands. So at a time I require R0 and R1 to be added. That means the 2 registers, if I put the output on the bus, they will combine, they will lose the data. So no significance for the data. That means that's why in a single bus organization, they provide one temporary register. They provide one temporary register that is called as a register called as a Y register. So this Y register is connected to the processor. So what is the purpose of this Y register? This register, whenever we want to perform addition of 2 numbers, first we'll bring the value into one of the registers into the Y register, so which holds the data temporarily. So then we can direct another register to the bus, so directly, and it's connected to the B. So Y temporary register is required to hold one of the operands among the 2 operands because single bus is there. So that is why we require Y temporary register. Similarly, ALUs are very fast. Within a fraction of a time of a clock cycle, they can able to finish all your addition and subtraction everything. We have studied that CLA adder and everything will take 4 units of time. You should not confuse with the 4 clock cycles. It's not a 4 clock cycles, 4 units of time. And that each unit of time is nothing but what? Propagation delay of the gates. That means that within a clock cycle, within a fraction of a time, your all operations can be completed. The moment you give the two operands, within a clock cycle, your addition is also completed and you should be able to place the data back to the processor. You can able to put it. But the problem is, since the bus is used to carry one of the operand which is placed on the B, you cannot put the answer back into the register simultaneously. That's why again I require one more temporary register which holds the data at, that is the result of the ALU temporarily, because ALU do not have the memory. ALU is only computation element. It's a combination circuit. It does not have a memory. So one temporary register is required. So which can put the data into the bus. So I have written this connection is required. Many times we know that a program counter is a one which is automatically should be incremented by a number so that it can point to the next instruction to be executed. We're assuming for all practical purposes the one word of a memory is 32 bits and the memory is byte addressable, in the sense that means that program counter should increment by +4 to point to the next instruction to be executed. Why? Because 4 bytes are required for storing one instruction. So where is the next instruction is located? If the first instruction is 0, the next instruction is located at the 4th address. That means that program count has to be incremented by 4 every time you finish the instruction execution. That means that this increment should happen during the execution of instruction execution itself. So in the sense, I require either an incrementer is required for a program counter. In older systems, in a single bus organization, generally, what they use, the ALU itself is used to add the number 4. That is why sometimes ALU is used to add the 4 itself to the program counter. In such cases, what we do is they introduce what is called as a multiplexer in the organization. So what is this multiplexer will do it? Either it will take a Y operand or sometime constant 4 is supplied here into the part of the multiplexer. Then there is a select line is available. This select lines, if we say select 4 means this 4 is selected and given to the here. If we say select Y, that means that it's a, let's say first is 0, other is 1. Select Y means the Y is comes to the E. That means that this multiplexer 2 to 1 is used. So either to select 4 or the Y and given to the ALU. So when the 4 is selected, whenever I'm adding the program counter 4, ALU is used to add 4 to the program counter and then put the answer back into the PC. When I'm not using to update the program counter, always the Y is connected to the ALU. So these are the connections what is generally present inside the processor whenever we design using a single bus organization. So basically we perform a lot of data transfers between the registers, or we perform addition and put the answer into the register, or we bring data from the memory and perform certain addition or swap operation. That means that these set of registers and the ALU and the path and the set of connecting wires which makes it happen is called as a data path. So data path is a word we are using to indicate the structure what is provided to execute an instruction. So data path is a collection of registers, the ALU and all the connecting wires which makes it possible for establishing the register transfers or memory transfer and executing the program. So this is a single bus organization, also we call it the data path for a single bus organization. Now we have understood now how exactly the different blocks inside the processor interconnected to make the things work. Now we have to implement little more details now. Now I want to know that how register gets connected to the bus. What is the way I can make the register, instruct the register to send the data to the bus? What is the way I can instruct the register to receive the data? So that means that there should be some facility should be there inside the circuit which enables only a particular register get connected to the bus. There should be some facility. There should be some facility or control is required in the circuit. Only when I send that control, only the bus should be connected to the particular register. So we will see that what controls are provided for each of these blocks so that I can able to give instructions to each of the blocks in what sequence the instruction to be executed. Now let's go to the registers. Now one of the option. Now we'll go to the registers. Let's say how register can connect to the bus. Let's take one register now. There are n registers are there. I'll take one register. Let's say Ri. Ri is a one register. It can be R0, R1, something like that. Now let's say this is a bus. This is a bus where it's get connected. I'm just expanding only that section. I'm expanding this section now. So now the Ri is a bidirectional in the sense each of the registers can be written or can be read. But at my control, only when I say read from this register, you should be able to read from the register and put onto the bus. Only when I say write into the register, at that time that register should be allowed for writing. That means that you should not be permanently connected to the bus like this. If you can permanently connect, then what will happen? All registers permanently connected, the data will be collide. So I don't want permanently connected. Only when it's required should be connected. That's why I'll introduce what is called a switch. So what is the switch? A switch is nothing but electronic circuit, a digital circuit, which acts like a close or open. How do we implement such circuits? So there is what is called as a buffer. ICs are available in the market. This is not an inverter. It's called as a buffer. So this buffer is also called as a tri-state buffer. So tri-state buffer are extensively used in the industry whenever we want to implement a switch-like feature. So all these buffers will have one control signal will be there. One signal will be there, which is called as a control signal. All the buffers. Normal inverters will have one input and output. What does a tri-state buffer will have? It has got a one input, one output, separate, one control is there. Whenever the control is equal to 1, it is a switch is closed. That is, whatever the input you give, it will be carried to the output. So whenever the control is equal to 0, then what will happen? Switch is open. That means that it's physically disconnected. So tri-state means that means that the buffer will have two states here. Normally that is when the data is input is 1, output is 1. When the data input is 0, output is 0. What is the third state? It's called high impedance state. High impedance state. High impedance state is called as an open state. It's nothing but an open circuit. Whenever you put the buffer into high impedance state, it is physically disconnected from the line. This is the way you can control whenever you require, enable a line to be connected to the bus. Whenever you don't require, just make it not connected. So like this, I'll put on buffer, tri-state buffer, I'll connect to here. Similarly, the register can also be written also whenever required. So I'll put one more buffer. I'll just give a connection to here. It can be buffer and a multiplexer. We will see that. You can implement by both the methods. Now, so these buffers are activated by a control signal. So that means that some circuit, which circuit generally instruction decoder circuit should generate small control signals, which makes it open or close. So we will call the name of the signal. Since it generates number of signals, I'll call a name for the control signal, which is generated by the processor, generated by the control unit inside the processor. So that names will be referring for the different buffers. Now I'll call name this for this as RI, that is I register. So I am writing out. So RI out signal. Now onwards, if I use, what does it mean that? So that is output switch connected to the ith register or ith register. So will be controlled by the signal. When RI out is equal to 1, that means that RI is connected to the buffer, connected to the bus. Similarly, there's one more control signal called RI in. So whenever I generate RI in signal, that means that whenever it's 1, that means that bus is connected to the RI register. Whatever the data present in the bus will be written to the RI register. So these are the two control signals which are required for every register. Now there are 32 registers are there. So 32 into 2. So 64 control signals will be there. Each two control signal will control writing or reading into the registers. Now we'll go to little more details into this one. If curiosity just makes you to know what is this register, how to design the circuit. For example, let me design the CPU in a simulator. Then I should know that how this particular circuit is being designed. So let's take one bit of a register now. A register will be 32 bits. Now I take one bit. How to implement this one bit logic? So we know that every register is nothing but a set of D flip-flops, because D flip-flop is the one which can hold one bit of information. So now I will implement now one bit of this logic. Now, so I will take one D flip-flop, Q and a Q bar. Now, let's say this is the bus. This is the bus, one line bus I have taken, one line bus. Now, so whenever I require, I should be able to connect the output of a register to the bus, so that I will use one trace type buffer directly and connect to the bus. So the one which controls that one control is called as, we know that the bit, whichever the single bit will take, that bit RI out. This is one bit. So we can implement using a D flip-flop. But whenever I require, I should be able to write into the D flip-flop. When you are not writing, whatever the value present in the D flip-flop should be retained. That is why I take the Q output. I want to connect to the D flip-flop input, because why? When we are not interested, you should hold the data. You should not lose the data, because why? The clock is a common clock signal. Let's say it's all active edge triggered flip-flops or edge triggered clocks are commonly used to design the process. So when I say clock is supplied at one place in the processor, every block will get the clock. That means that, so when the clock is given, if you're not writing the new data, whole data will be retained. That means that sometimes the data should be given by the queue, sometimes the new data should be able to come. So that means that there are two possibilities are there. So I will use a 2:1 multiplexer. So one is this data, other is this data. That is, I'm pulling the data from this one and it's connected here. So one which controls this one is nothing but RI and input. That means that RI in signal will control this multiplexer. Whenever it is activated RI in signal, that means that you are copying the data from the bus and writing to the latch. When RI is not activated, by default, the same data will be returned into the D flip-flop, so that data will be held. Like this, we can able to design the circuit for one bit of the register by putting 8 or 32 such blocks. I can able to design so this particular logic. Like this, we can design the logics of every block what is present in the processor by using the fundamental components. What are the fundamental basic components? Multiplexers, decoders, I can able to design it. So now I have understood how to design the register file inside the CPU. Now, so now I'll go to the next logic, how to design that one. Now let's take an example of, so the memory, let's say MDR register. Now I've taken the, now general purpose, all the registers. I'll take, what are the control signal required to control MDR register? We know that MDR register is a bidirectional. That means that I can write into the MDR register from the processor, So bus, I can also read from the MDR register into the processor. So that means that this is the processor side. This is from the processor bus. So this is the memory bus. This is the memory bus. That is external bus. So external bus, that means that I can, what is there in the MDR register, I can write into the external bus. So a switch can be given to control that. So this switch control is called as, I can call as MDR out external, out E. Out E means it's a one which controls the external connection, MDR to this one. Similarly, I can write one more connection with a switch, so which is useful for reading from the memory bus, external memory bus. So the controller for this, I can call this as MDR in external, I can call. So now there are two buses are there. So internal and external bus. Similarly, when I want to write from processor bus to the MDR, I can call the control signal as MDR out. Similarly, for this, it's called as MDR in. So now, so 4 control signals are there for MDR. Because why 4 is there? Because it's a bidirectional. I have 2 inputs, 2 outputs. If there's only 1 input or 1 output, you have only 2 control signals like other register. Only for MDR, we have 4 control signals are required now. Similarly now, so now we will see that what control signals is also required for the other side. So let's go back to the ALU section. So in the ALU section, we have an ALU available, that is A and the B is available. So here we have the Y registers available. Similarly, the Y is connected directly to here, but only thing is input to the Y is through control, through a control. This is called as Y in. So now another control signal is called Y in. So which whenever I enable the Y in, then only the data will be returned to the Y temp register. So it is other way. It is not to the B. It is to a through a multiplexer. Through a multiplexer, it's connected here, and it's connected to here. The another input to a multiplexer is a constant, the 4, and the one control for this is called as select. So select is one control signal. Y is another control signal. We have it. Similarly, so whenever we want to, the B do not have control. B is directly connected to the bus. There is no switches required. Whenever we place the data on the bus, it almost always comes to the B path. We don't require any control there. Similarly, so we have another register, temp registers available. Whenever I require, I want to write into this one. So that's why one more control is required. So this control is called as Z in. I can write it. Similarly, only when I require, I should be able to write this into the bus, internal bus. So this is called as Z out. So now I have identified all the control signals which are required to operate the different blocks what is present inside the processor. So now if I go back to this, look at the diagram. So similarly for the PC, so I can have a control, so a control signal is required to write in the PC. We call it a PC in. Similarly for the MER, we have two controls are there. One is MER in and MER out. MDR, we have seen that. For all the registers, we have in and out is available. For the ALU, we have studied Y in is there, Z in, Z out is available. So now almost we have the control signals we have identified for all the different blocks what is present in the processor, so that at my request, I can able to enable any of the blocks for writing. I can, on my control, I can able to enable any of these blocks for the reading. So these different control signals are generated by instruction decode and control logic based on the instruction which is being stored in the instruction register. Now we will go a little more detail how exactly instructions will be executed based on these control signals. Am I audible? Am I audible?
Audible, sir.
Okay. So now we will continue for some more time. So now we will find out what all the different operations or different phases or different sub-steps required in any instruction execution. So for any instruction we want to execute, any instruction execution involves the following steps is required. Number one, so we call it a fetch phase. The second is called execute phase. Any instruction will have these two phases for the completion of the instruction. In the fetch phase, we have to fetch the instruction from memory. So how do you fetch that one? We know that program counter is the one which contains the address. We will do this operation, program counter, and bring this into instruction register. This is the first step what we do. So contents of the program counter will be sent to the memory address bus, and then from that location, whichever you are referring, you are bringing the contents and bringing into the process and loading into the instruction register. This is the first step you do it. Then after that, increment the program counter, by 4. If you assume that 4 bytes are required for one word, so program counter will be added by 4. That means that, so these are the two steps which are required in the fetch phase. What does the execute phase execute? So perform execution of the execution of instructions. So when I say perform execution of instruction, a lot of meaning is there. To perform execution of instruction, you may require to fetch few more operands from memory. You have to do that job here. And then after fetching all the required operands into the processor, you're supposed to execute the instruction by giving an instruction to the ALU to tell whether it's an addition, subtraction, everything. Then after instructing the ALU to do the jobs, then you have to store the answer. That means that what are the 3 steps required in execution? Fetch all required operands. If the operands are already in the processor, you don't require to fetch. So this is only the if required. Then what is the second one? Perform the operation. So what is an operation is supposed to perform? You have to give the instruction to the ALU based on the instruction what you fetched. So instruction is already there in the instruction register. The moment it's there, you can understand what type of instruction you're supposed to perform. So based on the information what is present in the instruction register, instruct the ALU to perform the operation. Then, so what is the last step is store the result. Store the result. You can store the result either in the memory or in the register itself. So these are the three sub-steps required for the execution. So totally any instruction you take it, any instruction, always every instruction requires these two phases, fetch phase and execute phase is there. So other concept, any instruction if you take it, any instruction you take it, basically all the instruction can break into some fundamental operations. So fundamental operations. So in the sense, if you look at all these subtasks, this task, this, all these tasks, you can break down, that is all these operations, into 4 fundamental operations. Sometimes it can be more also, but basically 4 is good enough to describe most of the instructions. What are the 4 fundamental operations? Number 1. So register to register transfer, you may require to do register to, so register transfer, you may require to do it, or sometimes register to ALU transfer also you may be required to do it. That is, you're bringing from the register to the ALU to perform certain operation. So you may require to perform some operation from the, you require to perform certain, some operation and store the result into a register, You require to perform the memory read operation. So memory read means you are reading either instruction sometimes, or sometimes you will be reading an operand from the memory. This is one of the basic operations required. Sometimes what is called as memory write operation is performing. So we are writing data into the memory. That means that most of the operations will fit into this category. So either register to register transfer, or fetch the data from a register, perform an operation, store the result, or get data from the memory, or write in the memory. So now we will see that how each of these basic operations can be implemented by giving proper controls to the different blocks present inside the processor and make the things work for that. We will take simple small operations before we go to the full instructions. Now, let's say I want to transfer the data from register R3 to R4. Let's say this is my requirement now. So this can be one operation of this instruction itself. When I say move R3 to R4, basically it involves what basic operation? So R3 to R4. So now this is the job I'm supposed to do it. Now, what are the registers involved here? I'll write a bus. Now R3 is involved. I'll write R3. Now what is involved? R4 is involved. I'll write the R4. Now this is the bus. Now R3 is connected to the bus using one switch. So again, it's connected to the bus by another switch. Every register will have 2 controls will be there. So here also I have a one switch, and I have connected to another switch. I have just connected to here. Now the 2 controls for this is called as what? I'll call as R3. So if you want to write, we say in. Similarly, R3, other is out, and I want to read from this. Similarly, R4 I can call as in, and then I call as a R4 out. So these are the control signals which are required for me to complete this operation. Now what is an operation I'm supposed to write? Now the whole of these operations, whatever there inside the processor, can be completed in one clock cycle. Many of the operations inside the processor, we will assume that it can be completed in one clock cycle. And also we assume that it's an edge triggered circuits are used inside to complete the operation. So within one clock cycle, what are the things I can do it? I should be able to move from R3 to R4. That means that data what is present in R3, I want to write into the bus now, So that whatever the data, so that instruction is R3 in is the first instruction I'm going to give it. This is basically a control signal. The moment I give this instruction, the data in R3 will come to the bus. Now, the data what is there in the bus, simultaneously you can write into the R4 register also, because in one clock cycle, both these operations are possible. So what should I give another control signal? R4 out, I give it. Now, so this is called as step 1. It's a basic step 1. Now this one single step is good enough to complete this operation in this case. So like this, we have to identify what are the small tasks we can complete in one clock cycle. When I say task, it is nothing but what control signal you're supposed to generate, which in turn controls and activates some operation. So what are the controls? The sequence of instruction, sequence of control signals are instruction sequences I supposed to generate R3 in and R4 out. So like this, I can able to finish the basic operations. So now let's go to the, so another 5 to 10 minutes, I'll conclude. So now I'll go to the another operation. So which I want to perform. It's now what I'll do is I'll take a little bigger operation now. Add R1, R2, and the answer is stored in the R3. I supposed to do it now. So now I want to perform addition. In the previous case, I am not perform addition. I just move the data from register to register. I understood what are the control signals supposed to give it now. Now I have to identify how many steps are required or how many clock cycles are required to complete all the steps required to perform the execution of this job. Now what is the job? I have to add, I'm not considering now fetching the instruction from memory. I'm just considering adding R1 plus R2 and then putting the answer back into R3. That is my job. I assume that already all the instruction is there inside the processor. I want to complete it. Now steps. So step number 1. So first I have to bring R1 into the ALU. We know that in case of ALU, so we have what is called as a register called Y is available, which brings the data through a multiplexer and connects to the bus called A. At the same time, so all other registers are connected through the bus to the B part, and its output is connected to a temperature called Z, which has got a one control, which has got another output control, and then it's connected to a bus. So let's now write the instruction for this. What is the first step? I want to bring R1 into the ALU. That means that I said we cannot bring both the data simultaneously. That is why this temporary register called Y is available. So first I will give the instruction so that the contents what is present in R1 register. So contents what is there in R2, I have to bring into the ALU now. So first I'll bring from R1 to the Y register. Now there is a control available here. There is also control is available here now. So first I should enable R1 data should come into the bus. So that is nothing but R1 out. Now at the same time this data I can write into the same clock cycle into the Y register. So what is the control here? It's nothing but Y in. So I just written Y in now. So now this data whatever comes here, it comes into the A if proper select line is given here. So assume that the proper select line is given. So it's nothing but select Y. Select Y means so the Y input of the multiplexer is being brought into the A. Now both A is available data, both the B data is already B data can be made available by enabling one of the registers here now. Now this is all I can do in the first clock cycle. So in the first clock cycle, what I can do is I can just bring in the data from one of the register into the Y register. So one clock cycle is completed. The next clock cycle, what I can do it. Now already the data is available. One of the data is available here. Now I should bring in the data from the R2 register. Now R2 is available. I will just bring in the data to the bus B. So I will enable R2 out. Now the data comes automatically. It's available where? It's now available. It's available at the B bus. So instead of select Y, we can give it here. We can give it here itself because it's required addition. Only when addition is required, I can enable the select Y. And now, so since in the second clock cycle, both the data is available and within a fraction of a time of a clock cycle, addition is performed. I have to give instruction to the processor. That means that add operation is supposed to perform. So now what I will do is I'll give instruction add. When I write add here, it is nothing but the control signal generated by the decoding or control circuit to inform to the processor, that is ALU, what operation is supposed to perform. Now addition is performed now. After addition is performed, you can push the data into the Z because all this can happen in a single clock cycle. So I can say Z in. So in the second clock cycle, you brought in the second operand. First operand is already available there and you perform the addition and store the answer into the Z. So all this can happen at a single shot. I cannot bring the data outside of the Z to the destination register R3 because why? The bus is used to carry the R2 data. So now third clock cycle is required. So what the third clock cycle is required? Now the data what is available in the Z, I should able to enable the Z out and make it to write into the R3 register. I should able to write into the R3 register. Now what should I do it now here? I say Z out. That means that output of the Z will come to the bus and then enable R3 in. So I'll just write R3 in. So now what will happen? The data is there. So these are the fundamental steps, or called as control steps or control sequences, required to make the execution of this instruction once the instruction is available inside the CPU. So like this, we have to identify what are the basic steps are required to make the instruction execute by using the different blocks. Only if I identify these basic steps, then we can able to design a hardware circuit, and we can design the decoding circuit, how the control signals can be generated and what sequence it has to be generated in every clock pulse. So this is the way we can able to design the fundamental control sequences for every instruction for a single bus organization CPU. So we'll continue tomorrow. So any doubt, I'm available for some time.